My title of my talk today is Multi-Scale Numerical Modeling of Storm Surge, Tide, and Inundation in the Mid-Atlantic Bight and New York City during Hurricane Sandy 2012. I'm co-author with Giorgio, Joseph Zhang, Linus Magnuson, Derek Loftus, and David Forrest. My outline, first I will talk about large-scale storm tide modeling using three-dimensional barotropic schism in the Mid-Atlantic Bight. And then I will do the sensitivity test. Three effect, atmospheric forcing, 3D versus 2D formulation, and effect of coupling with wind wave model will be addressed. Number three, I will also use street level subgrid modeling for urban inundation in New York City in conclusion. First, large-scale storm tide model. The model uses schism, semi-cross-scale hydroscience, integrated system model. The key feature highlight are several of them, but I will highlight that this is an unstructured mixed grid, and then it is polymorphism, meaning a single grid can mimic 1D, 2D, and 3D configuration. I also want to emphasize this is a semi-implicit time stepping, and therefore is not restricted by CFL stability constraint. Lastly, I also want to indicate that the bathymetry do not need to be smooth because of the use of spatial vertical axis coordinate. And this is a model grid. On the left-hand side, this is a model domain. It's covering entire US East Coast, Gulf of Mexico, and Caribbean Sea. You can see the tidal open boundary is set in the at 60 West, which is from Nova Scotia to South America. On the right panel is US East Coast unstructured grid, and on top of it, red showing all the NOAA tidal gauge station that will be used for comparison with model. First, we did astronomical tide simulation. Given the boundary about 1,500 kilometers away, we want to see if astronomical tide can be simulated properly, and it does. Example of the battery in New York, the R square is 0.96, and the statistic of all the tidal calibration in the station is listed here. Is quite proper. The next thing that is what our interest is storm tide simulation, and this is showing the Hurricane Sandy track. Start with the A, B, C, D is the time track, the hurricane track prediction by different model. Notably, ECMWF is shown by the coral, and which is the first model predicting the track will be turned 90-degree left. And this is an animation of a Hurricane Sandy. And you can see it start with Florida in the US coast, and then it's go north and then turn left 90-degree into the New Jersey coast. So to simulate this storm tide, we need set up a schism for use. I will highlight that we did the 5-day spin up and then 5-day forecast. And the runtime for this 10-day simulation is 80 minutes on their infinite HPC resources. The wind forcing is crucial, and we are using two atmospheric model field available. One is North America name is North America medium range atmospheric model. And then ECMWF is the European Center for Medium Range Weather Forecast. And the figure, you can see the observation is shown by blue, and the name wind field compare near the station show on the right hand side corner, right up right corner, just off the New York City coast. And the orange show is ECMWF. You can see that the name has overshooting and undershooting near the peak period from UTC 15 to 10, October 30, 3 o'clock in the morning. And orange is shown by ECMWF, and it hover around the observation better. And this is a storm tide result for the station, night station showing measured by the NOAA tidal gauge. We use the red as observation and blue as a schism modeling, and that is 3D-W-E means using three-dimensional formulation barotropic model, and W means coupling with a wind wave model, and -E means ECMWF. This is the best simulation we were able to get. And it starts with Montauk, New York on the Long Island Sound, and through Long Island Sound to Kings Point, New York in the upper panel. And the middle panel is from the Battery, Sandy Hook, New Jersey, and Atlantic City, and then coming down to the New Jersey and Chesapeake Bay and Dock, North Carolina. The statistic is showing on this table. The mean average of this R square is 0.965. Mean absolute error is about 10 centimeter, and relative error is about 15 centimeter. So the second part of the talk is about the sensitivity test. And we have three factors. One is 2D versus 3D formulation. Number two is coupling with wave or without wave. And then the atmospheric using ECMWF versus a name. So in here, this figure is using the Battery in New York as an example. You can see there's an upper panel that is using 3D formulation. And so this is a 3D, and the bottom panel is a 2D. And during the peak, there is an insert box that's showing the detail of the difference. So in this time series comparison, we do see that using the 3D coupling with wave using ECMWF as forcing has the best skill, which is R square equals to about 0.96. And comparing with the other scenario, for example, 3D-WM means three-dimensional wave coupling by using name, and also 3D-E means without coupling with wave. And then at the bottom panel, 2D with wave and ECMWF. And then on the right, lower panel is 2D with ECMF and name without wave. Right. A little more detail, this is the effect of 3D versus 2D formulation. And you can see that with coupling with wave at the left has a better simulation peak is much better. And in terms of wind wave modeling, we are presenting the standalone comparison of significant wave height, and the bottom panel is peak period. The significant wave heights go up to close to 10 meters during the event, and the peak period is somewhere between 10 seconds to 15 seconds. So this is a wave model was actually modeled and coupled with storm schism. And this panel showing coupled with wave on the left panel with the 3D get the best result compared with the 2D on the right-hand side. So the third part of the talk is about street level subgrid inundation modeling. So having successfully modeled the large-scale storm tide, we still need to deal with street level inundation in the local in New York City. So the main focus of the subgrid inundation is how much is the inundation extent on the land, and also the timing of the inundation and how much the depth of inundation. On this subgrid modeling, we have two key features. One is we use a covariance formulation, which allow the flow transport information to be transferred between computational grid and the subgrid analytically. And then secondly is a nonlinear semi-implicit solver for tracking wetting and dry process. This is a technique developed by Kozuli and Sterling. The reference is at the bottom. So this is an example of subgrid. So we develop a separate grid in the Long Island Sound and New York City, and on the top panel. And then the lower panel, you can see that what is the subgrid versus the base computational grid look like. And so the bottom panel showing the South Manhattan Island is being digitized with a subgrid. So base grid is a 200 meter by 200 meter, and subgrid is a grid subscale and within the base grid. So it is a 5 meter by 5 meter resolution here. And so to set it up, this model we call LSEC sub model domain. And I have, so that panel showing the base grid on the top, and then the subgrid in the Kings Point, near the Kings Point. You can see the subgrid in there. And to set it up, it turns out there is a 36 million sub-element in here. So to run this model, similar the boundary condition is needed, south and east, and then atmospheric forcing and simulation period start from October 22nd to November 1st, 2012. And this is using, again, using the HPC resources of 80 core of subcluster. And it can, when you simulate 10-day simulation, it takes 19 minutes. And for a subgrid included, and without a subgrid, it's taking 60 minutes. So with subgrid is because it's using analytical transfer information, only takes 3 more minutes. And the result of the subgrid compared with USGS on land gauge, and this is a comparison. The red is the measurement, and blue is model result. So the result is fairly good. On the bottom right panel, you can see the measurement flat out at a certain height, but the model was able to go through the entire depth. And in addition, this is the water level measure and model in the Kings Point. So the top panel is NOAA's tidal and current measurement. It's showing the blue is astronomical tide and green is actual measurement height. And the surge is a difference of the two, and which is shown by the red line. And this particular feature rise 2 meters in three hours, and it's the highest storm surge during the Hurricane Sandy, and reach about 3.9 meters. And this feature was able to simulate using LSEG sub in the bottom panel, and the blue line showing that it was able to show the profile of this rising, and also the timing is almost exact, only a 10, 20 minutes difference. And lastly, the important information is for subgrid modeling is to look at the inundation extent. And this panel showing that the A is all the inundation in the New York City, and then B, C, D, E showing the FEMA's inundation map compared with LSEG sub. And further, we compare the detail of near the Manhattan, and the left panel is FEMA's, and the right panel is model. And this is from area point of view, it catch about 80% match. So this conclude my talk. The conclusion, there are 5 points. Number one, that 3D barotropic unstructured grid schism model was coupled with wind wave model and successful applied in Mid-Atlantic Bight and during Hurricane Sandy. The overall model performance is quite favorably. The maximum absolute area is about 0.1 meter, and the Lumen square is about 0.14 meter. And second point is comparing using a different atmospheric model name and ECNW show that ECNW obtained better result than those using NAM. Number three is 3D mode versus a 2D mode. And we think 3D mode doing better because of the two reasons. One is it's resolve the boundary layer induced shear stress rather than use 2D's bar vertical average velocity. And number two is that 3D model can have a distribution of velocity in the vertical and can account for this interleaving dissipation process important near shore. And number four is a sensitivity test with and without wave. And the wave do contribute to the total water level, is spatially and temporally varying and increased water level on the order of about 5 to 10% of the total water level. Lastly, the LSEG, this subgrid model was applied to simulate inundation in the New York City. First, we showed a time series comparison with USGS on-land deployment gauge, and it's quite reasonable. And specific, the model was able to accurately mimic the steep rising water level profile and catch the timing of the surge at King Point's New York, which is the largest during Hurricane Sandy. In terms of a spatial distribution, the inundation extent generated by LSEG was matched about 80% of FEMA's inundation map, which is created based on interpolation of the major 80 high water marks. In the end, I want to point out the future work. The 3D barotropic model was able to accurately predicting the upmoving trend of the storm surge until the peak of storm tide. However, the model over-predict the water level immediately after the peak of the storm tide for a duration of 1 to 2 days. presumably due to the coastal set down as a result of volcanic response of the coastal ocean to the changing wind field from predominantly northerly to southerly wind. To remedy the deficiency of 3D volcanic, I emphasize volcanic instead of barotropic coastal storm surge is desirable in the future. Thank you.